So let's move to the last speaker of today's session, Pieremanuele Canepa. Dr. Canepa is an assistant professor in Material Science and Engineering Department at National University of Singapore. His research focuses on applying first-principle calculations to investigate the complex structure of liquid electrolytes and electrode interfaces and diffusions in materials for novel energy storage materials. Dr. Canepa, all yours.
Okay, good afternoon. Can you hear my screen? Can you see my screen and hear my voice?
Yes.
Okay, good afternoon, everyone. Good morning, everyone. Good evening, everyone. We are spanning in a number of time zones, and it's a great pleasure to see how many participants. Let me acknowledge the organizing team, particularly Rosie. You were great at coordinating everything. Malaki and Professor Doron Harbacher for this nice invitation. I'm based at National University of Singapore in the Material Science Department, but also hooked up with the Singapore MIT Alliance, which is a presence here in Singapore. And today, my talk looks at understanding interfaces in multivalent batteries. It will be mostly dealing with magnesium battery. We have other activities in sodium and lithium ion nowadays, but this is what my talk is about. And we use techniques related to first principle computation, in particularly density functional theory and beyond. But why multivalent ion battery? Well, on the left-hand side, you have a typical prototype of lithium batteries, graphite anodes, oxide cathodes, and this is the best that you can get in the market. And everything sandwiched in an electrolyte, a liquid electrolyte. Well, on the right-hand side, you have at the half of the size, you have a magnesium battery. The good feature there is that it operates on a metal anode, so you're not using an intercalation anode. And on the cathode side, in principle and in theory, this is just theoretical, because you're shipping magnesium 2+ every time, you can ship 2 electrons. In reality, this doesn't happen. It has been shown by Professor Harbach around 2000 that yes, indeed, you can use a metal anode with specific electrolytes, but the intercalation cathode is really the limiting aspect. And Professor Harbach and Linda Nazar recently, initially Professor Harbach proposed a Chevrel material, which is this molybdenum sulfide or selenites. And more recently, the group of Linda Nazar showed us that titanium disulfide can intercalate as well magnesium, and very efficiently. However, because you're using a sulfur or even suffering more selenide-based chemistry, your open circuit voltage is rather small. So the idea is to, of course, use a compact oxide here, and however, the compact oxide has some limitation, especially because it brings your positive voltage, or the OCV to very high voltage, and this has a negative effect on the electrolyte, which have typically a very rather small anodic stability. And so the electrolyte that we have been dealing nowadays are rather limited in their electrochemical windows. So again, just to summarize the problem here, we have a very peculiar reductive chemistry of magnesium, which also is a great scavenger of oxygen. As a matter of fact, you form very easily magnesium oxide and magnesium hydroxide if you don't control very well the oxygen and water content in your glove box or whatever the environment will be. And yeah, if you were to use high voltage cathodes such as V2O5 or chromate or other spinel that have been tested in the literature with various results, well, then you will be still limited by the oxidative stability of this electrolyte that you could use, which are stable against the magnesium metal anode and not against the cathode. So how do we go about solving this problem, or at least identifying a couple of pathways that could be helping us in solving these issues? Well, path number one, we can envision to coat coat electrode materials with a specific salt, and we will see how we do that. And strategy number 2, we try to understand the decomposition product of this liquid electrolyte, and we reverse engineer, meaning that we find a combination of liquid electrolyte that will decompose at the interface, releasing phases that are electrochemically stable, so they don't conduct electrons, but they can transport very well ions. So 2 pathways in summary. The strategy that we use is not new. It has been modeled on the work of one of my ex-colleagues. Unfortunately, is not anymore in academia. It's a great loss, Will Richard, when I was back in Berkeley and MIT. This technique is very simple. It uses the chemical potential of magnesium in this case, but if you were to use lithium or sodium, or if you were to work on sodium or lithium battery, it would be the equivalent of a chemical potential of magnesium and sodium or lithium as a proxy for voltage relative to a magnesium or whatever the intercalation ion reference is. So what you do is just to develop this thermodynamic function, which is called ground potential, which now depends on the free energy. This is the free energy of your compound, but at variable magnesium chemical potential. So the ability here is that you can fix the magnesium chemical potential at specific value, and then you look at this ground potential phase diagram that which informs you on the stable phases as a specific magnesium chemical potential, hence voltage due to this equation. And of course, we can use computational material science to compute these thermodynamic quantities, such as the Gibbs free energy, magnesium chemical potentials, and hence this ground potential phase diagram, which allows us to map the stable phases as specific voltages. And just to give you an example, this is a material we worked in the past. I don't want to spend a lot of time here, but this is on the left-hand side is a computed phase diagram. So a beauty of computational material science is that you can compute stuff, and this phase diagram I find them particularly useful to elucidate a specific question in general. But this phase diagram, as you can see, as the 3 elements composing this phase, this magnesium scandium selenide, that at that point of time was our interest. But you can clearly see that this compound is a spin between two compounds here, magnesium selenide, a binary, and scandium selenide. And another thing to note is that this compound never share a thiolane with magnesium. So this compound already, by looking at this phase diagram, we could clearly see that it's not stable against magnesium metal. But let me put in action the ground potential phase diagram that I showed you just before, which is remapping the free energy at the variable magnesium chemical potential. And what you see here is obviously a reduction of coordinates from a two-dimensional phase diagram. We pass to one-dimensional phase diagram. The only variable here is the scandium fraction. It doesn't matter too much. But what you should pay attention are this number here. These are the voltage versus magnesium. And now you can see that at the 0 voltage, meaning that you are at the voltage of the magnesium metal electrode, the phase, the desired phase that we were looking at that time, magnesium scandium selenide, is not here, right? As you go to more positive voltage, starting from 0.25 all the way to 1.25, this phase is now present, right? So this, what is the result of applying this ground potential formalism here to this system? The result is twofold. One, you get the bounds of your stability windows, which are basically the highest bound at the lowest voltage is the cathodic stability windows. So you have a position relative to the magnesium electrode or whatever electrode will be of your reducing stability windows. And then you get an anodic stability windows. And the difference, of course, between these two voltages gives you the window span, the electrolyte stability windows that is commented in the literature. So let's apply now this technology to a number of materials or chemistry or a wide chemical space in general that might be interesting when you're looking at the composition product of a liquid electrolyte in a magnesium cell, or if you envision to go the other way, coating electrode, you might envision to synthesize material and coat the particles of your electrodes so that you can form specific phases containing magnesium metal. What are the hypotheses? The hypothesis is that, well, we have looked at binaries, ternaries, and selected quaternaries. And more importantly, these are all experimentally reported. So there is no Fanta chemistry here. And the second hypothesis, I apologize, is that none of this chemistry that we are looking into contains redox elements. So this is because if you have a redox element, a change in oxidation states might signify that you move electrons across your potential coating material. So in summary, this portion of periodic table summarized that we look at trials, specifically boron complexes or materials, carbon, silicon, germanium. We have the picogens, the chalcogens, and the halogens. Of course, the active ion of search here was magnesium, but you could in principle apply to sodium, lithium, whatever. And we also look into hydrogen containing compounds up here. You will see why. So let's apply this technology to a number of materials. It starts with a very simple example. We have halides here plotted. On the x-axis, you have the voltage versus magnesium. So at 0 is magnesium metal, and as you go to more positive voltage, you're reaching the voltage at which ideally one cathode would operate. Let's set ourselves at 3 volts with the magnesium chromate. And immediately you can see, if you look at these halides, and by the way, these numbers are the electrolyte stability windows computed. All of these material are stable against magnesium metal. This is not a surprise. At the same time, there is something important to notice, which is almost quite intuitive, is that as you move down the period of the halide, the stability windows shrink. And this is related to the electronegativity of the halogen. We can extend, obviously, this to more material, and the same behavior operates for oxide and chalcogenides, right? With magnesium oxide being the most extended in terms of stability windows. Again, these materials are all stable against magnesium metal. And the story changes slightly when you move in other groups. So in summary, there are some interesting opportunities here when one looks at this material, especially when it comes to halides or sulfide, selenide, and telluride. But let's move to ternary and quaternary oxide. The situation is significantly more complex here. Again, at 0, you have the reference of your magnesium metal, and the voltage grows with respect to the x-axis, mimicking the potential voltage of a cathode. What you see is that none of this bar touches the magnesium metal, and there are some that gets closer, but still, this is a very important information, because for oxide, as I'm showing you here, none of these oxide will be stable against magnesium metal, but they often decompose in magnesium oxide, which is naturally detrimental in terms of what a magnesium battery can do, right? When you have magnesium oxide on these electrodes, well, it stops the percolation of magnesium ion. Now, at the cathodes, there are some interesting chemistry that could be rather stable, meaning that the anodic stability windows sits at relatively high voltages. And so you can have magnesium borate, magnesium silicate, magnesium phosphate, and aluminate. And importantly, some of this material have quite a large stability, oxidative stability cutoff. So in general, oxide might not be super important when it comes to the anode side, but they could be interesting from a cathode side point of view. What we have is also, we have computed ternary and quaternary for selenide and telluride, and as well as a hydride, which might be interesting, and we might discuss it later. But let's rationalize with some phenomenological models what are the observation here. So at the high voltage cathode, let's say V2O5 or magnesium chromate, yeah, the governing things process is that you're trying to extract electron from the electrolyte, right? So or from a potential coating material. So if you look at the stability windows, or particularly the anodic stability windows that we observed, are correlated with the Pauling electronegativity of the anion. This is not surprising, right? If you have an electron tightly bound to a specific species like oxygen, it's much harder to extract this electron or effectively oxidize the coating or the electrolyte by this mechanism, right? So moving down the group of a specific category, chalcogenides, halides, and so on and so forth, halogens, sorry, your stability windows is, anodic stability windows is bound to decrease. But more interesting becomes like the aspect of reducing reductive stability or cathodic stabilities near the anode side. And here I'm showing you particles of potential coating material or the composition product. So here, the process that we are witnessing is the insertion of electrons. Effectively, the magnesium metal anodes sit at a very low potential that is able to insert electron and so reduce whatever is nearby. What we find is that if you're looking at ternary or quaternary materials, the Pauling electronegativity of the non-magnesium cation, and let's say you have a compound that contains chlorine in addition of magnesium or oxide and sulfur and phosphorus in the format of a phosphate, then your phosphorus in a phosphate acts as a cation, then the stability, the anodic stability, cathodic stability of the composition products is inversely dependent on the Pauling electronegativity of this cation, right? So it's effectively the ability of your cation of not being oxidized. This is actually quite important because you can envision a material in which you put a sacrificial cation, such as phosphorus, that might inhibit the reduction of magnesium. Another aspect that is slightly more intricate when you look at the composition product at near the anodes is that there is some chemistry that tends to get reduced very easily if the binary of connected to the ternaries has a strong formation and has a definitely a highly thermodynamically driven formation energy. So if you look at, for example, this series of germanate, including oxygen, sulfur, or selenium, you can see that reductant stability of this material increases as you move from oxygen to sulfur to selenium. And this is because there is a strong tendency of your chemistry to develop magnesium oxide over magnesium sulfide and magnesium telluride and so on and so forth. So the stronger dependency or attitude of your material towards the formation of binary systems that are extremely stable, such as magnesium oxide, penalize your reducing or cathodic stability. The interesting part, though, is that so far we just touch upon the electrochemistry and perhaps the thermodynamic aspect, right? But one of the major challenges in magnesium battery is the transport of these multivalent ions. So the real challenge in multivalent batteries, so any ion beyond 1+, so sodium or lithium, is to transport them in a lattice of oxygen or an ion typically. So it becomes really an electrostatic problem because you're moving a 2+ charge in a cage of oxygen ion or sulfur, and it's this electrostatic interaction with the anion. It's a significant problem. So we try to solve these issues by looking at the transport properties of these coating materials or the composition products, put it as you want. The phenomenological model is not very difficult. We can control 3 variables in our computational experiment. We have time, we have length, and by length, I'm talking about the cross-section of the material that is coating your electrodes. Here is magnesium electrode, but it could be a cathode. And then you have temperature up here. So if you set this parameter saying that I discharge my battery at a certain C rate and I coat my electrode, or I hypothesize that the thickness of my deposition is a certain amount of nanometer, and then you set the temperature of your experiment, you can, from a back of envelope calculation, define a maximum tolerable migration energy. And so this is rather easy. This allows us to set some bounds, right? So these are very optimistic bounds, but of course they set up like 2 extrema on which everything else falls in between. So you can think of having a particle that is 50 nanometer in thickness, or the thickness of this coating layer is 50 nanometer, and discharging your battery very fast at 10 C. This is obviously not a real condition, and temperature we keep it standard at 25 degrees C. What you get is a rather maximum barrier which matches more or less to 600 milli-electron volts. Now you can have the other ends of the spectrum where you think that you have a rather thin coating and you discharge slowly. This is not super slow in magnesium batteries, but it is still not very fast. And we keep the temperature for comparison at 25 degrees C. What you see is that you can tolerate a much higher barrier, 990 MeV. So this very much sets the 2 ends of the spectrum, and everything else in terms of thickness size or discharge rate falls in between. But before I move on, let me show you a whole video of mine when we were looking at electrodes, and this is just to elucidate how we compute the transport of ion in this material. So we start, this is magnesium V2O5, you have 2 layers stuck on top of each other, and these are vanadate layer. The oxygen are those coordinating this gray ion, which are vanadium ions, and in between,
2 more minutes.
Yeah, I'm almost done, thanks. And in between you have a magnesium anode in its typical position. Now, when we start the simulation, and you will see the ion now moving if everything works. Looks like we are, okay, so it's moving. Now, as magnesium get coordinated, you see the atom on the top, they are connecting the magnesium. This represents the migration activated states, depending if you have chemistry or the migration energy, and then magnesium move to the nearest neighbor site, having translated by 1 lattice vector. And from this type of analysis, we can figure out the barrier for transport, migration barrier, which related to macroscopic quantities, right? If you were to do an impedance or some other transport measurement, for example, through solid state NMRs, as we've seen a few talks ago. So let's look now at some of the chemistry that we have identified. So on the x-axis, I'm showing you the migration barrier. On the y-axis, the number of materials. And what you see here are my 2 boundaries that I set: 600 MeV for a thick particle but fast discharge, 980 MeV as a maximum tolerable barrier for thin layer discharge rather slowly. And you see that the survivor are very few materials. You have here some halides, some hydrides. Some of the material here have low barrier below the blue barrier, but then when you look at the electronic conductivity, which is here just summarized in terms of bang gap, then they are a good electronic conductor, and this is not a desired thing. You might be surprised, not surprised to see that magnesium chloride forms, which is a compound that forms in one of the most common electrolyte used in magnesium battery, well, conducts ion in an okay way, right? So it is well known that magnesium chloride precipitate in this electrolyte, perhaps the MAC or some other magnesium aluminum chloride electrolyte. So it's important to show here that the transport properties of these halides and magnesium chloride are rather good. There are other compounds that appears here. Magnesium hydride seems promising also in terms of stability against magnesium metal. At the cathode side, the situation look a little bit less promising, because we can identify very much two materials. One is the magnesium aluminate, which by the way is not stable against magnesium metal, and likewise the magnesium phosphate. The magnesium phosphate is interesting because it has a rather large band gap as every phosphate. If you think about acetone or other phosphate that do not contain transition metals or open D, right, system. So in summary, I've shown you a work that summarized the work of 2 years on computing and understanding the decomposition product of more than 100 compounds. The techniques is very general, can be applied to lithium and sodium batteries. We have identified some materials that might form upon the composition at the anode. The halide are definitely one. The hydrides are promising. One rule of thumb that one can put in place is to, when you look at ternaries with respect to the anode, and so cathodic stability windows, is to look at compounds that have a sacrificial non-magnesium cation, but this will not work for oxide because you form this magnesium oxide. For high voltage cathode, one strategy could be to implement this phosphate material and perhaps illuminate. I have my concern here, but this might be interesting. Recently, this technique has been applied also to a work that has been done and spearheaded by Alexander Pondrush in Barcelona, and particularly by his PhD students, Hoha. The results of the application of this technique that I show you are midway promising. I cannot say that are 100% promising in comparison with what is observed experimentally, but it's worth for you to check this article if you're interested. And let me thank my colleague, assistant professor, is a baby assistant professor, Sai Gautam, and Tina Chen, who's still a PhD student at University of Berkeley. And my sponsor, the National Research Foundation here in Singapore, Ministry of Education, obviously NUS and SMART for providing cash and resources. And thank you very much. I will be delighted to answer any question.
Thanks, Piero. So you have 2 questions. Can you quickly go through them?
Yes, give me a second because I cannot see anything here. Okay. I cannot see the question actually.
You can see them?
Yeah, let me stop sharing perhaps. Yeah, okay, I have 2 questions.
Yes.
Okay, one question is which computational method has been used? Yeah, in one of the slides, really tiny, we showed that we were using GGA. So we used standard PBE. At that point in time when we were developing this, this work, we didn't, scan wasn't available. Hybrid and GGA plus U, I mean, there is not much reason to use them because we don't have any transition metal or at least open D transition metal. What is the role of anion doping? Yes, this is a very important in the facilitating magnesium transport. Yeah, this is a very important point. The defectivity is entirely neglected in this calculation, and So it's at this point in time, I cannot answer proficiently this question, but I think is a very valid point, as in every calculations that have been done in the past in batteries in general. So the validity of the defects and the role of defects at various level scale in terms of length is really crucial and fundamental. What is the shell size in computing phase diagram? I don't understand what is the shell size. Perhaps it's a cell size. If it's a cell size, we are looking at a primitive or conventional cell. Thank you very much.
Thank you, Piero.
If you have any questions, you have my details. Thank you.
Thank you all. So we are an